And now, diving into the world of scalable AI infrastructure. Our next speaker is someone who thrives at the intersection of data, infrastructure, and intelligent systems. Mr. Prabakaran Kumaresshan brings over a decade of experience in data wrangling and building robust data products, and is currently immersed in the world of platform engineering. Known for his passion for solving complex problems with elegant tech solutions, Prabakaran's expertise lies in bringing the gap between experimentation and real-world development. Today, he'll be taking us into a session titled Productionizing LLMs on Kubernetes. He'll walk us through the process of deploying and scaling large language models using Kubernetes, tapping into its powerful orchestration capabilities to manage containerized AI workloads in a reliable and efficient way. With that, please join me in welcoming Mr. Prabakaran onto the stage.
Hello. Am I audible? Hello. Yeah. Thanks a lot, Sweta, for the introduction. So I know it's after a lunch session. I just want to kickstart this, talk with a bit of questions, because some of the topic we're going to cover today is going to be, it's an intersection of things, right? Like, so quick raise of hands, right? How many of you used LLMs in your local or in server, right? Nice, good. And how many of you have used Kubernetes? Okay, good. I think I have a critical mass to kickstart this, talk, I guess. So we are coming to a full circle right now, right? Like with this talk, what I'm trying to, kind of do is, how do you bring LLM to your Kubernetes, right? I know this is kind of advanced topic at this moment, because a lot of people are right now using hosted, API-based service, and still there are very few set of people, like in banking industries and others, who are really wary of their, data privacy and user content, right? Only they are like self-hosting their LLM at the moment. I'm sure in some sense in future, like all of us would run into this kind of problem, or at least you are not running the entire LLM, or at least you will run a small language model, right? With that, let's go. So this is pretty much the agenda that we're going to cover today. So we'll start with a bit of foundation. The topic that we're going to discuss today is called LLMOps, right? We'll delve a little bit on that, and then we'll talk about the orchestration layer, which is our Kubernetes, and why Kubernetes, etc. And then we talk about specific inference runtime engines, and then how do you scale those LLMs with those inference engines. And then we'll quickly delve into some of the LLM AI platform that is available for us to use, and then we'll quickly check the observability metrics as well. So yeah, so far what we talked about in this the entire day is about kind of a data science part, and then we also talked about some of the experience from a solution as well. So what we're going to try and delve into is a bit of operation side of those things, right? I know you might have heard bits and pieces about this throughout the other talks, but we're going to try and see it from a fresh perspective. So LLMOps is not something very new, but it's been there for a while. I hope you all know about DevOps, right? Yes. And then there's something called something that was there. Was MLOps. So these were there for your traditional machine learning workloads, right? But and then after the LLM, the advent of LLMs, we have a new field of operations, that is LLMOps, right? So you might wonder, is it new wine in old bottle? Maybe not. I'll try to justify that, right? Why LLMOps is different from the traditional MLOps, right? Some of the things, the model size, and then the infrastructure required, right? So if you were, has anyone worked with traditional MLs, like for instance regression models, classification models? Cool. So those models, like you kind of pickle the file and then like slap it on top of a simple API server, maybe Flask or Fast API, and then like you can call it deployed. the way that you want to productionize LLMs are very different. Many of them demand a GPU to, kind of get you a realistic, inference time, right? And then the serving complexity, right? Like I talked about, right? You don't really need a inferencing engine for traditional ML algorithms for the most of them. With LLM, you cannot achieve any scale or like performance unless you have a very fine-tuned, inferencing engine. So that's where it is different. And then the data pipeline, right? For a traditional MLOps, you had your feature engineering, imputation, etc. The data pipeline that you have is very different. But for LLM, there is you have either RAG or some agentic workflow, right? The way that you handle the data is entirely different. There is less of pre-processing in LLM. There is more of conditioning in LLMs. And then there's observability and monitoring, right? The way that you observe traditional ML algorithm is like how quickly you can get the response, what is the confidence score of the algorithm, etc. But for LLMs, the observabilities are like your token at token level, and then how quickly you get the first token, etc. The observations are very different. And then comes your governance and compliance. With traditional ML, there is not much of governance in terms of model per se, but there were a lot of governance around the data, right? Where do you source the data? How do you, kind of version it? Like what kind of data gets into your model training, etc. But when it comes to LLMs, the governance kind of shifted to the output side, right? What is your LLM is, kind of giving you the output? Is it toxic? Do you need to moderate your content? Is the output, is within the boundary of your context, right? Let's say, for instance, you're building a customer support. Nobody is like prompt injecting it into, kind of translate something French to English or something like that, right? You have a lot of governance and things on the output side of your LLMs. And then your, experiments and iteration. How do you build traditional MLOps is like every now and then when you have enough data piling up, when your model is, kind of drifting or you have data drift, you kind of train the whole model there. But with LLM, the opportunity to retrain the entire model is not there. Either you do some kind of fine tuning or, even the iteration is like a RAG model. You might want to re-invalidate your indexes and then update your vector DB. The entire experimentation workflow is entirely different. I hope I justified why LLMOps is very different. Cool. Next up, we'll talk about a bit about Kubernetes and why I believe it could be the orchestration layer for ML workloads. So Kubernetes is very famous for giving you, out of the box construct for your workloads. There are various types of workloads you might want to use, right? For instance, you want to have a chatbot or something always up and running. You could go for a pod which is always up and running, right? Or you might want to do, kind of do a CronJobs every now and then, right? At certain point in time, you want a bot to wake up and then kind of do something. You could go for a cron job, or you want a bit of more dynamism to your, your workload in terms of you want it to be, fast, right? As and when the request comes in, you want the model to wake up and answer it. Something that Knative can do with the function as a service model. And then there is constant workload, right? You have a lot of incoming requests. You don't really want to answer them right away. For instance, you have some kind of ML workflow that kind of reads your email and does on top of it and then kind of summarize it, right? You could provision a constant workload of GPUs with KQ, and then you can queue all your data into it, and then your workload can process it at its own sweet time, and then kind of turns out all your output there. So Kubernetes serves all kind of different workload needs that you might encounter. Up next, like how do you deliver your solution, right? For starters, it's very simple. You kind of create a Docker file and then kind of dump it there, and that's like very simple way of delivering a model. And then comes your Helm chart, right? Let's say your application is slightly more complicated. It has some certain initialization script to be run, or even when it is shutting down, it needs to do few more things. For instance, in case where you are like bringing up your workload just in time to serve and then like going back, like it needs to do something before and after and things like that. You can package them as a Helm chart and then, you know, kind of slightly deploy a complicated workflow there. And then comes your operator. Anybody aware of operators in Kubernetes? Cool. So operators in Kubernetes like kind of peeling another layer of Kubernetes, like basically you are plugging straight into your Kubernetes API. So Kubernetes is very powerful. Operator model in Kubernetes is basically leveraging your Kubernetes API. It can do a lot more things. It gives you more power to do. Like for instance, like for some reason, right, your workload kind of goes out of memory. How do you recover your workload? And then in case of your updating, right, like you have, let's say, Llama 3 running, and then you want to push another update, Llama 4 or something like that. How do you quickly, you know, smartly update all those, you know, workloads behind the scene without affecting? Because the problem with LLM is, like, let's say for instance, right, you are running an agentic workflow, right? Agentic workflow, it kind of goes through a chain of thought. It's not like your traditional update, like you cannot just kill a pod and then bring it back because something is already chatting there, right? It goes on for a while. You need to wait for that agentic workflow to complete, only then you can insert another one, right? There are a lot of smart decision needs to be done in your deployment. That's where your, you know, operator kind of helps you there. Cool. We'll talk about inference engines. That's a bit of a crux for today's. How many of you heard of vLLM? vLLM is very different from LLMs. Cool. So vLLM is an inference engine, right? So in LLM, you know, there is Llama, Ollama, etc., right? Can anyone say what are they? Just technically, what are they like? When Meta comes up with, you know, says Llama 4, what is it? What do they mean? Sorry? Exactly. So we kind of, you know, term it wrongly, right? Like they are not open source model, they are like open weights model. Nobody is, you know, kind of telling you how they train the model and what data they trained on, right? They are like open weights model. So all you get is just the, you know, black box of weights that you can, you know, kind of deploy and, you know, inference it. So, so that's where LLMs are very different. They are built differently, and then the way that you infer them, like serve them in you know, server, you need entirely different, you know, kind of framework to serve them. There are quite a few in the market, but why I'm rooting for vLLM is that, one, definitely it's open source. It came from UC Berkeley, and it has a lot of industry heavyweights behind it, you know, kind of optimizing the entire code. And obviously it is vendor neutral. I think in the age of AI, it's very important to have someone who is vendor neutral, because with being vendor neutral, it's not about you're, you know, discriminating against one vendor or other. It's just that being vendor neutral means you get to have all the capabilities from all the vendors. So you can always switch to one or the other, right? And since OpenAI pretty much led the way, vLLM kind of supports a thin wrapper around the serving engine, which is compatible with OpenAI. Cool. Don't focus too much on the, you know, diagram per se. Just wanted to quickly give you an understanding of how inferencing really works here, right? You have a proxy API server. I'm really sorry, the texts are really not visible. So you have 3 layers here. There is a proxy API layer. This is basically your, you know, kind of slash complete or slash embedding. If you have used, you know, OpenAI, you know, client, those are the, you know, web interfaces, the API layer that you have. And then within vLLM, there are like 2 layers. They kind of go to and fro, but what you need to understand is there is something called prefill state, and then there is a decode state. Prefill is basically you're decoding your tokens, and then once decoded, it goes into that, you know, kind of a sequencing, and then like you get the next token. So basically next token prediction, right? And it goes back to the prefill, and it goes on and on, right? Like that's what you see here. So this is just keep this in mind. We might need this in future, right? So yeah, enough of talking, right? How do you use vLLM? It's very simple. What do I mean by offline inferencing? Is basically when you run it in your local machine, right? That's all it takes, right? Import vLLM from LLM, and then kind of you can give bunch of prompts to it, and then you can load any compatible models. Pretty much most of the popular models are compatible with LLM, and then all you can do is just vLLM.generate prompts. You give the bunch of prompts, and then you get the output. So that's as simple as getting vLLM to up and running in your local. And then how do you serve it on server, right? The way that you could do is you start a vLLM server, something like this. You tell vLLM, and this is serve. For instance, here where we are using Qwen 1.5 billion instruct. Once you start this, it starts the API server, a thin wrapper around the inferencing engine, and then this is at your client level. So from your local, you could use OpenAI libraries. You don't need a separate client library to interact with vLLM, because it provides a OpenAI compatible interface for you to interact with it. So all you have to do with the OpenAI client library is just replace the base API. You replace it with whatever is your server URL, and then you can talk to the the model just like you would use a OpenAI. So it's like a drop-in replacement for OpenAI. Cool. What else, right? I think we in our industry we go through this cycle, right? We go through the software optimization and then hardware optimization cycle. What do I mean by that is, like, at some point in time people are very invested in how do you optimize your software for the given hardware, and at some point in time we hit a plateau, like, okay, that's the best we can do for at a software layer. Okay, let's go back to the hardware and just kind of make it better. So I think that's where we are here right now. So at least in the last few years, most of the researchers went towards compiler optimization and things like that. Now people have realized that we have kind of hit that plateau of how much you can use the hardware, and the next innovation is happening, at least the one that we are not aware right now and happening, is pretty much every big internet giant, they kind of working on their own kind of custom accelerator. The NVIDIA, the one that we all know of, and then AMD ROCm, it's something that is consumer grade, and then Intel Arc is something it's been around for a few years right now. But behind the scene, there are a lot of custom chips are coming up for AI acceleration. Intel is working on Gaudi, and then AWS is working on Neuron. Google TPU is something that has been around for a while, but it's not widely adopted. At the same time, we also have some of the advancement happening around ARM architecture as well. So vLLM pretty much supports all of these architectures. That's again the advantage of being vendor neutral, right? They adopt whatever is the fastest hardware you have. vLLM would have a implementation for you. So you can be very flexible with what accelerator you kind of use, and the one that works for you economically. All right, is vLLM the only inferencing engine? Not really. You might have used in local, Llama CC, C++, and then, Ollama. And then other production grade, inference engines are like your TGI from, Hugging Face, and then TensorRT LLM. And then a few more are there. But vLLM is kind of popular because it's very flexible in terms of supporting the hardware and the kind of different optimization which is something we'll look at. Cool. These are just a small chunk of optimization that vLLM offers. There is a big laundry list, and I'll quickly kind of talk about some of them. Quantization, automatic prefix caching, and distribution interface. So the optimization sort of happens at two levels. One is how do you optimize the existing model, what best can you do with the model level, and then there is another thing called runtime optimization, right? So a model optimization, a quantization is one typical example of optimizing your model, where I'm not going to delve deep into the technicalities of it, which is something already covered by Preeti and others. So quantization is basically you are trying to quantize your model. Basically, you lose some kind of accuracy, but your model becomes really lightweight. What that means for your inferencing and your inferencing hardware is that you're gonna need a smaller footprint of GPU RAM, which is very expensive these days. Yes, you kind of lose a bit of accuracy. It's something, a decision that you have to make when you are kind of doing this kind of quantization, whether that kind of accuracy loss is okay for your application or not, right? While it also supports quantization, it kind of gives you one of the fastest I mean, like, for quantization you need certain kernels. vLLM supports something called Marlin. Do read about it. And then there are a lot of quantization methods, right? As an inferencing engine, you need to support a lot of inferencing quantization methods, which are like FPA, int, and GPTQ, AWQ, and then bits and bytes, something that we talked about earlier today. And not only that, it also provides you with some compression toolkit, which is like you already have an existing LLM that you want to kind of quantize. There are some tools available for you to quantize it yourself. Cool. Now that's about your model optimization. Now let's talk about runtime optimization. So now you have a model. Now you're kind of starting it. What can you do in runtime, right? There are problems that you can solve when you are actually in production, right? Let's quickly look at some of them. So automatic prefix caching. I know it's quite mouthful. What it simply means is that when you kind of interact with some of those agents, right? For instance, let's take customers service chat interface sort of thing, right? This is something you may not have heard. How many of you heard about system prompts? You know it as a concept? Good. So what system prompts are, like, when you kind of interact with any chatbot, even though you're typing your query, when it actually hits the LLM, there are two messages. One is something called system prompts. It basically says, hey, you are a nice customer service representative. You are very helpful. You know your thing in your domain, whatever it is, your medical or something. And then here's the query from the user. So system prompts are like pretty much, they are like baked in. The LLM kind of sees the same prompt again and again. For every user query, it gets the same prompt and then whatever the user types. So in runtime, you can totally kind of optimize for this, right? You know for a fact that for every request, you're going to keep getting the same kind of text. You kind of optimize it, right? So what we do is, whatever the LLM, remember there is a prefill and then there is a decode phase. Prefill is something that the same set of text needs to go back again and again. What you could do is you could cache at the prefill level, and then for a decode level, you can just, for these texts, you can directly go to the decode level instead of doing the prefill text. So that's one. And also there is a multi-step conversation, right? When you start a conversation with a LLM, it's not that whatever is your current query, it's not that the only thing that goes to your LLM. It also the entire history, so that it has a context of what was the conversation throughout, and then it kind of answers your question in its context, right? Which also means that every time you fire a new query, all the previous query gets bunched up and then it is sent to the LLM. So LLM sees the same thing again and again. So again, there is a bit of kind of optimization you could do with these repeated text. So again, you could save a lot of compute power there in the prefill state by caching it. That's basically what your automatic prefix caching does. Cool. And then there is a problem, right? Like, I don't know how many of you try to kind of provision a GPU in AWS or somewhere else, usually there are different classes of GPUs, H100, A100, etc. Right? Usually you get an older generation of GPU at a really nominal price from a cloud provider, rather than taking the recent one. But what's the trade-off you're trying to make is the older version or generation of GPUs, they come with a very smaller RAM, maybe 12 GB or something. But much of these LLMs won't accept that kind of small RAM footprint. They need a bigger chunk of RAM. But you can go for, either you could go for a latest version of GPU which can give you like 60 GB or 100 GB, etc. But they're very expensive because they are latest generation. You pay for the opportunity cost. What you could do instead is you could attach multiple GPU to an instance, and then you need to shard your LLM workload across multiple GPUs within a node. Or even if that is not enough, you could take multiple nodes having multiple GPUs, and you can shard your workload across multiple nodes having multiple GPUs. That is something we can effectively do with vLLM. That way you can save a lot of cost at an inference by just using a very old architecture GPU. So that's something you can achieve with LLM, but you do need something called RayServe. Ray is kind of a Python library for distributed computing. You just need to enable that. With Ray, vLLM can get you that distributed inferencing. This is pretty much you achieve it. Let's say you have a single node, multi-GPU, one node, let's say AWS instance with multiple GPU. Let's say for instance 4 GPU, you would just start your LLM server just like this, and then automatically it starts sharding your workload across 4 GPUs. And then you have still your LLM is not the memory is not enough for your LLM. You could serve it across multiple nodes with multiple GPU. With that, your workload is again shared across multiple nodes. Cool. I'll quickly go through some of the ML platform, because vLLM is an inferencing engine. You're gonna need a kind of ecosystem to build your entire ML platform, right? These are some of the LLM platforms available. Basically, they have baked in vLLM as part of their core engine, and on top of that, they would have built different nice aspects that you need, as like for instance, right? Consider like your Django or Spring Boot. It has some things that you essentially need for every application. That's what they bring in. What you choose among this is up to you. There are a few things that each will kind of excel at. For instance, the RayServe is very good at distributed stuff. Cool. I'll quickly walk through some of those observability metrics that you might want to look at for a LLM. So one of them is latency breakdown. So unlike a typical request response, with LLM you are like continuously generating tokens, and then you are like getting it. So one of the first metric is that what is the time to your first token. Once you punch in your query, how much time it takes for your first token to arrive. A lot of time this is very important, because if you have kind of provisioning just in time, your infrastructure is not always up. That determines what is your cold start time, and then once you start that query, and then how long it takes for the next set of tokens to come in. That's a different thing that you can track. And then obviously GPU utilization, right? Because they're very expensive. Tracking their utilization kind of helps you save on the different infrastructure costs. Cool. With that, I'll conclude. So this is typical metric that you can monitor. Cool. So that's me. Thanks everyone for your patience. So